Okay, so this video is entirely on partial fraction. So first, let us see that when do we use partial fraction? Now, we use this method of partial fraction to integrate a specific type of integral. That is, if my integration is of the form, this is a special form. If the integral is of the form px by qx dx, where px and qx, they are polynomial functions such that degree of the numerator function px should be less than degree of the denominator function qx. So this is very, very important, the most important part, that in order to apply partial fraction, you have to ensure that the numerator polynomial has a degree strictly less than the degree of the denominator polynomial. Now, if it doesn't happen so, then what to do, that I will discuss at the end of the video. So for the time being, we will assume that all my sums satisfy this condition. Okay. So now, assuming this, now once we ensure that this condition is satisfied, we know that I can integrate this by using partial fraction. But then, depending on the nature of qx, here the important deciding factor is qx, the denominator polynomial. Depending on the nature of the denominator polynomial qx, we use various methods of partial fraction. So that is going to be the second point. So that is uh, depending on the nature of qx, we apply different methods of partial fraction as discussed below. Okay. So now let us see what are the various types. In the first type, if the denominator polynomial qx can be expressed as the product of some linear distinct factors. So this is the first type, that is the qx, the denominator function. You have been able to factorize it and express it as the product of some linear distinct factors. So if such is the case, then what method we will apply? How will we do the partial fraction? So each case I will discuss with the help of an example. So let us take the example, say my I is 2x plus 6 by x cube plus 4x square plus x minus 6 dx. So first of all, we observe here the degree of the px, that is numerator, is 1 and degree of denominator is 3. So the required condition has been satisfied. But before proceeding, we also observe that we can take a 2 common. So this is very specific to this sum. You may not be able to do so in other sums. So since it can be done here, let us do it. So 2x plus 3. Now all of you know how to factorize a cubic polynomial, so I'm not going into the details. So you will get x minus 1, x plus 2, x plus 3 dx. Now incidentally here x plus 3 get cancelled. So ultimately it becomes 2 dx by x minus 1, x plus 2. So this is the final form. We redecorate the integral in this form. That is the denominator as product of factors. Now the rule is, let, now in the final form of the integral, that is the last stage, excluding the dx expression, whatever you have. For example, here we have 1 and denominator we have x minus 1, x plus 2. So we take that part. So just removing dx, excluding dx, we take 1 by x minus 1, x plus 2. This we write as, now one alphabet for each linear distinct factor. So the first factor here is x minus 1. It could have been written in the other way around, x plus 2 into x minus 1. Doesn't matter. So a by x minus 1. So one alphabet a, that is constant, for one factor plus b by the other factor, x plus 2. So here if you do the LCM, so this is x minus 1, x plus 2, and a into x plus 2 plus b into x minus 1. Now if we compare this portion and this portion, then we can write, since their denominators are same, we can write 1, their numerators will be same then. So 1 equal to a into x plus 2 plus b into x minus 1. Suppose I name this relation as 1. Now my sole aim is to find the values of a and b. This can be done by two ways rather. Since this sum where you have linear non-repeating factors, you can simply put x equal to, you choose such a value of x that will be convenient for you. For example, if I choose x equal to minus 2, then this will vanish. Or if I choose x equal to 1, the second portion will vanish. So that will help me to easily find the values of a, b. So putting x equal to 1 in 1, we get 1 equal to 3a. So a equal to 1 by 3. So I found the value of one constant a. Similarly, putting x equal to minus 2 in 1, we get 1 equal to minus 2 minus 1 minus 3b. So b equal to minus 1 by 3. So I now know the values of both my constants a and b. So if I put back the values of a and b uh, here, that is, I put back the values of a and b in this step here. So substituting a and b. So what is the I then? What is my I? What form does it take? Now, if you look at the final form of I that I had rearranged it into, that was this. So, 2 integration. Now, excluding dx, 1 by x minus 1 x plus 2 has been expressed as a by x minus 1 plus b by x minus 1. So, inside the excluding dx, whatever is here, that has been actually split into two parts. That is a, which is 1 by 3 by x minus 1 plus b, which is minus 1 by 3 by x plus 2, and then dx. So what we are simply doing is we are expressing first we will express qx as product of linear factors, then the entire integral in the form of factors, we split it into two different terms and find the values of the constants ab. Then we put back the value of ab, and then the integral looks like this. And this becomes integrable very easily. So now this becomes, remember there is a 2 here. So 2 by 3 integration dx by x minus 1 minus 2 by 3 integration dx by x plus 2. So that is very easily, it is easily done. It is log mod x minus 1 minus 2 by 3 log mod x plus 2 plus c. Now leave your answer here. Do not try to simplify this further using the properties of log, because that is not part of integration, that is optional. So even if you don't do that, you get full marks. So this is the main thing. So just for discussion's sake, let me also add here that suppose instead of it might so happen that your qx, you had to express it as product of say three factors or four factors. Here we had ultimately two. So say x minus a, x minus b, x minus c, x minus d. Though such a I mean such situations rarely occur, maximum you can get is 3, but still I'm taking 4. So in that case, when you write your integral, that is the integral function excluding the dx, so in that case it will be your px by qx is actually px by these four factors. So then you write it like this: a by the first factor, b by the second factor, c by the third factor, d by the fourth factor, and so on. So the process remains, and then we follow the same process. So this is just to show you that you use one alphabet each for each factor. That's all. So this is first, and probably that is the simplest type, this type 1. Now let's go to type 2. Now what is type 2? Type 2 is somewhat similar, but the only difference is here in the first case your qx, the factors that you obtained by factorizing qx were all linear and distinct. Here the factors will be linear but may not be distinct. That is, some of them may be distinct and some may be repeated. So that is the second case. So here what happens is qx, I'm just trying to write it into short. Qx is actually product of still linear factors, sum of which may be repeated. Okay, so here the main thing is, first of all, they are linear and some may get repeated. So if such a situation occurs, then how will we do the sum? Again, let us take an example and do it. Say, one second. Okay, here I named it A, so I should have named it B here. Sorry. Second case is B. Okay. Now again, let us take an example. Say you have your integral is I equal to 3x minus 2. So that is my px, and x plus 3, x plus 1 whole square dx. So here the denominator qx has already been given in the factor form. If not, then you will have to factorize it first. Now in such a case, what will we do? Let the integral, that is 3x minus 2 by x plus 3 x plus 1 whole square equal to. Now here you can see there are two distinct factors here, x plus 3 and x plus 1, of which x plus 3 is not repeated, but x plus 1 has been repeated. So the factor for which there has been no repetition, that is x plus 3, will be treated exactly as in case A, that is 1 constant for x plus 3. But when you have a particular factor repeated, then you have to take one constant for each power of the factor. For example, here, let me write it here. You have x plus 1 whole square. That means the first power x plus 1, you always start with 1, power 1, and then you come to x plus 1, 2. You could also have x plus 1 3, but we don't have it here. I'll mention it later. So this is one occurrence with power 1, and then another occurrence power 2, which is the maximum that happening here. So first you take one constant for power 1. Always you have to start, no matter what power you have here, 2 3 4 5 whatever, the first constant will always be that for power 1. Then another new constant will be for the next higher power. Now we have to stop here because the sum has this power. Had there been 3, I would have written plus d by x plus 1 whole cube. So starting from 1, you go on increasing the power by 1 till you reach the power that is given in the sum, and one constant for each such occurrence. So that is the main thing. After that, the process is same. That is again LCM. So just like the previous sum, this implies that since this denominator and this denominator, oh, I'm sorry, by mistake I wrote this extra. Yeah. So since the denominators, these two denominators are same, so the numerators will be equal. So 3x minus 2 equal to a into x plus 1 whole square plus b x plus 3 x plus 1 c x plus 3. So suppose this is 1. Again, as before, putting x equal to say minus 1. in 1. What do we get? Now left hand side, 3 into minus 1 minus 3 minus 2 minus 5 equal to, acha. So this factor, these two factors will vanish, x equal to minus 1. So this is 2c, minus 5 equal to 2c. So from here you have c equal to minus 5 by 2. So one constant determined. Now let us put x equal to minus 3 in 1. So you get minus 11 equal to 4a. So a equal to minus 11 by 4. Another constant determined. Now you come across a different situation here because you don't have any more factors. X plus 1 and x plus 3 both you have utilized by putting x minus 1 and minus 3. Still there is an unknown factor, sorry, unknown constant, b. So in such a case, what we do is we equate coefficients of similar terms from both sides, that is left hand side and right hand side of 1. That is, you can equate coefficients of x square from both the sides, you can equate coefficients of x, or you can even equate coefficient of constant terms, that is the constant terms themselves. So that's the easiest part, equating constant terms from both sides. So equating, so when this is the this method that I did, you should first try this, and then if it does not suffice, then you go to this and then start equating the constants. That will be easier for calculation. So equating constant terms from both sides of 1. What do we get? Now on the left hand side, your constant is minus 2, and right hand side, if you see your constant term, from here if you apply a plus b whole square, a square is x square, 2ab will be x containing term, b square will be 1, and when you multiply that with a, that is a. So you get one a from this term, constant term a. Okay. Now from the second one, the constant term will come only when you multiply 3 with 1. 3 into 1 is 3, and then multiply with this. So 3b. So this is another constant term, 3b. And from the last one, you get a constant term when you multiply c with 3. That is 3c. So 3c. So you get a new relation of which you already know the values of c and a. So you can find the value of b. So if you calculate it, probably b will be 11 by 4. So this is how we get all the three constants. Now that I know all the three constants, I will put them back in this step. That is, the integral that I had, this is my integral, this is my integral. So now I will, instead of writing it in this form, I'm going to write it in this form, that is the split form, replacing the values of ABC. So my integral will look now like this. Therefore, my I is minus 11 by 4 dx by x plus 3 plus 11 by 4 dx by x plus 1 minus 5 by 2 dx by x plus 1 whole square. Okay, so these three are very easily integrable, so I'm not going into the details of the integrations how to do this, simply writing the answer. Okay, so these are the first two types. Next we will go to the third type, that is C. Just let me check what color I was using. Oh, okay. A, B, C, green. Okay. So the next type is C. Now the third type, C. Now here the integral is of the form px by qx dx, where qx can be expressed as the product of both linear and quadratic factors. Till now we were having only linear, either distinct or some may be repeated. Now qx will be product of linear and quadratic factors. For the time being, let us also assume that uh, they are not repeated. That is, uh, the factors are not repeated. Once I discuss this, I will also tell you in case in case of C, if the factors get repeated, then how to deal with it. So that will come to later. So let us take a sum. For example, say you have dx by x plus 1 x square plus 2x plus 2. So clearly you can see here that one factor is linear, this is linear, and this is quadratic. So in such case, what we will do? Let the integral, that is 1 by x plus 1 x square plus 2x plus 2 be equal to, now for the linear factor the rule is the same as we discussed in cases 1 and 2, that is one constant a for one linear factor x plus 1. But when we consider a quadratic factor, since the degree of a quadratic factor is 2, so we have to choose the constants in the numerator in such a way that the degree of the constant, the degree of the polynomial that we now consider in the numerator has degree 1. What I mean is, see, in case of linear factor, for x plus 1, degree is 1. So we have taken a constant a because degree of constant a is 0. So the rule is, whatever is the degree of the denominator, the degree of the numerator should be 1 less than that. So in case of linear, since the degree is 1, so we take just a constant because the degree is 0. But now, since we have a quadratic here, which is of degree 2, so we have to take the numerator in such a way that the degree is 1. That is, we have to have 1x. That is why we write it like this, bx plus c. So now if you see bx plus c, it is a polynomial consisting of two unknown constants bc, But ultimately, this polynomial is of degree 1 because the denominator is of degree 2. So there should be a difference of degree 1. So this is how you deal with quadratic factor. And then the rest is same. So that is LCM x plus 1, x square plus 2x plus 2. So A into x square plus 2x plus 2. Just hold on for a second. Plus bx plus c into x plus 1. Okay. So just as before, so this implies if you compare this and this, denominators being same, just the numerator 1 equal to a into x square plus 2x plus 2 plus bx plus c into x plus 1. Now, putting x equal to, just as I had put 1 and 2, I could put x equal to 0 also. So, if I put x equal to 0 here, in 1, x equal to 0, and let me name this 1, x equal to 0 in 1, what do we get? So left hand side is 1, so that remains unchanged, unaffected by the value of x. So 1 equal to, and right hand side you get 2a plus c. If you're putting x equal to minus 1 in 1, then what happens is the second expression on the right hand side vanishes. So only the first remains. So there you get a. 1 equal to a. Putting x equal to 1 in 1, what do we get? 1 equal to, now here right hand side if you put 1, then you get 5a plus 2b plus 2c. So there is only I mean, putting x equal to minus 1, this vanishes. Such a thing will happen only with minus 1. The factors are like that. So only in this case you get the value of the constant directly, a equal to 1. Otherwise you get two. See, you have three unknowns, you need to have three equations to find out the value of abc. So now, if you solve these three, I'm not going into the details of that. I'm sure you can do that. So, since you already know the value of A, you get the value of C. So, similarly, putting the value of A and C here, you will get the value of B. So, ultimately, you will get B equal to minus 1 and C equal to minus 1. So, these are the three values that you get. So what happens to my integral? So now this becomes, so I'm going to use this form, this expression instead of the given integral, where I will substitute back the values of a and b. So it becomes a was 1. So this is dx by x plus 1 plus b was minus 1. So minus b minus 1 into x minus x, and c minus 1. So minus 1 by x square plus 2x plus 2 dx. Okay. So now the first part is easy. That is log mod x plus 1. And for the second part, you just have to simply, take the minus out. So take minus common. And if you differentiate the denominator, then you get 2x plus 2. So we'll try to bring 2x plus 2 here, but then I'll have to multiply this with half because it is x plus 1 after taking the minus 1 out. So x square plus 2x plus 2 dx. So this manipulation, I think you already know how. This manipulation, you know that if the differentiation of this is actually of this form. Actually, I'm trying to this form. Integration f dashed x by fx dx. I'm trying to bring this form. Then we know that it is always log mod fx plus c. So that's it. That is precisely what we have done. So ultimately you have log mod x plus 1 minus half log mod x square plus 2x plus 2 plus c. So that is your final answer. This is your answer. Okay. Now, if you go to your NCRT exercise, then I'm sure you can find it. Some number, yeah, some number 9. Let's check out sum number 9 from your NCRT exercise on partial fraction. So this is another example. This is from your NCRT exercise. In my book, it is 7.5, sum number 9. So I won't do the whole sum, just discuss it. So this is integration 3x plus 5 by x cubed minus x squared minus x plus 1 dx. So if you factorize the denominator, then it will look like x minus 1 x square minus 1 so that is 3x plus 5 by, if you break this, a plus b into a minus b whole square, so ultimately you get x plus 1 x minus 1 whole square, right? So at this stage, if you look, it looks like a linear and a quadratic. But if you further break it, you see this reduces to type B. This becomes type B. That is, the factors are all linear. One is distinct, that is no repetition, and the second x minus 1 has a repetition of 2. So now you know how to deal with that, right? So this is how we deal with the denominator, that is a mixture of linear and quadratic. Now, if we had a repetition here, so let me add it like this here. So I'm not taking any particular sum, just uh, taking the denominator. Say your qx is like this. X plus 1, then x minus 1 whole square, and then you have, say, x square plus x minus 2. So it is a mixture of linear and quadratic with repetitions in one of the linear factors. So in that case, we will write my let px by qx equal to, so 1a for x plus 1, then 1b for x minus 1 to the power 1, 1c for x minus 1 whole square. So that's, we are done with the linear one. And then for the quadratic, we have to take a linear one up in the numerator. So we need two more constants. So we'll use d and e. So dx plus e for the quadratic one. Now, this is a very complicated situation. Usually, you don't get this in exams. I'm just discussing it so that it becomes clear to you in case such a situation occurs, what to do. And you might wonder that why I haven't taken the quadratic factor repeated. Now, if you take quadratic factor repeated, then that becomes very, very complicated, and you don't get that absolutely in your exams. So you need not worry about that. Okay, so that's with uh, type C. Okay, now these are the three main types, but remember I told you in all these types we made a pre-assumption that degree of uh, pre-assumption was that degree of the denominator px was strictly less than degree of the denominator qx. In all the above three cases, this was my assumption. Now, if the sum is given in such a form that this condition is not maintained, that means not maintained means if you have degree of px either greater or equal to degree of qx, then what will you do? So that is what we are going to discuss next. Okay. Let me take a sum, for example. Say you have x square plus 1 by x square minus 5x plus 6 dx. So here you see degree of px equal to degree of qx, both 2. So I cannot apply the rules of partial fraction here. So first we have to do the long division. Let me do it here. So x square minus 5x plus 6, x square plus 1. I'm sure you all know how to do this, but still I'm doing it. X square minus 5x plus 6, subtraction. So these get cancelled. So you have 5x plus 1 minus 6, that is minus 5. Now you see this is the remainder. Why? Because degree of this is 1, whereas divisor has a degree 2. So this is my remainder. This is my quotient. And of course this is my divisor. So now I can write the integral in this form, that is quotient plus remainder division algorithm by the divisor, x square minus 5x plus 6 dx. Then you will separate it. You can take 5 common if necessary. So x minus 1 by x square minus 5x plus 6 dx. Now this portion satisfies the required condition for partial fraction. That is, degree of the numerator is 1, degree of denominator is 2. Now you can proceed with one of the processes of partial fraction because it satisfies the condition. So, like similarly, if you have another sum that is there in your NCRT book, that is, this was sum number 9, which I did. Now I'm doing sum number 12. Here, the sum is x cube plus x plus 1 by x square minus 1 dx. Okay. So here also, you can just simply do the long division, split it up, and then do the partial fraction. Here you can see the degree of the numerator is 3 greater than degree of denominator qx, which is 2. So proceed as above, just a long division. And so these are more or less, not more or less, these are the types of partial fractions that you will have to deal with. But after this, I would like to do some special sums from your NCRT exercise. So this portion will, this discussion ends here. Then we'll go to some special sums. Okay, so now uh, I'm doing a sum from your NCRT only, exercise 7.5, NCRT, exercise 7.5. I'm doing sum number 18. Okay, let me first write the sum, then I'll tell you what is the speciality of the sum. Uh, so what is the speciality here? Speciality is both px and qx um, have only even powers of x. That's a speciality. See, both the numerator and denominator, they have x square. Now, how will we deal with this one? This is very, very important sum. Now, here, first we will do nothing related to partial fraction. First portion that we'll do is simply we ignore the integration sign, that is integration dx. We ignore it. We just consider the expression, consider only this expression outside the integration. Now here put x square equal to some other variable, say t. Then this expression becomes just instead of x square you will put t. So it becomes t plus 1, t plus 2 by t plus 3, t plus 4, which on simplification is t square plus 3 2. I hope I'm doing the calculations correctly. So you really need to check it once. T square plus 70 plus 12. Now here you see degree, in this expression you see degree of pt, that is numerator, is equal to degree of qt, that is degree of denominator. So we are actually uh, rearranging the integral in such a way that we can apply uh, partial fraction. So for to apply partial fraction, we cannot have degree equal. So naturally, after this, we will perform long division. So here we will perform long division, and then this becomes, after performing long division, it will become 1 plus minus 40 minus 10 by t square plus 7t plus 12. Okay. Now what we'll do is this portion, the second portion we will apply partial fraction. So let me write it like this: 1 minus 2 I can take common. So this becomes 2t plus 5 by t square plus 7t plus 12. Okay. Now I will take up only this portion and apply partial fraction. So let 2t plus 5 by t square plus, actually t square plus 7t plus 12, we go back to the uh, factor form. 2t plus 5 by t plus 3 t plus 4. We multiplied the factors to get this so that we can do the long division. Once the long division is done, we come back to the factor form because we need to see the linear factors and take the alphabets accordingly. That is a constant. So this a by t plus 3 plus b by t plus 4. And then proceed as before to find the values of a and b. So once you find the values of a and b, then uh, it will be I think it is minus 4, I think. Anyway, whatever it is, I don't want to do the calculation and waste time. So you can find the values of a and b, substitute them back. So once you substitute them back, then this expression is split up. That is the green circle, rectangle box portion. It gets split up into uh, this portion, this expression where you know the values of a and b. So now what happens is you replace, once you have done this, found the values of a and b, then you replace t square by x. You replace it back. Actually, by mistake, I said replace t square by x. It will be the other way round. It will be replace t by x square. So I'm inputting this audio portion to rectify my mistake. Okay. Then replace t square by x. So it was initially it was x. You substituted x by t square. So replace it back, and then your I becomes. Let me do it this way. So I becomes, so if you look at the I, the original I that is here. So this was your original I. Yeah, this was your original I. Okay. So the integral, you split it like this. The integral has been split. The original integral has been split into this form, and then that has been further split into this form. Okay. So from this expression, you will get your original I. So your original I will be integration 1 minus this portion I'm keeping under bracket, this portion, this whole portion, the second portion after the minus portion. So when you put the value of the values of a and b, then you get minus 2 by, you do the sum yourselves and check it out with whatever I'm writing, whether it's correct or not. My sole aim is to show you the process, not the calculation. 6 by x square plus 4, because I've replaced t by x square. Okay, right. So this dx. So now this is my original integration. So that splits into, so we see one thing, the this substitution that I had done here, this substitution x square equal to t, this I have done without the integration sign. I mean, it is independent of the integration. I've just simplified the expression so that I can apply partial fraction and split it up, and then I go back to x, and then I come back to the integration. So this is, finally it becomes integration dx minus, so minus plus 2 dx by x plus 3, then minus 6 dx by x square plus 4. So then you have to do the rest of the integration. So this is easy. This is easy, and this is a special formula. I don't know whether you have been taught this in class or not. Integration of dx by x square plus a square. So you can deal with that. So another similar sum you can do on your own. Similar sum, integration x square dx by x square plus 4 x square plus 9. Try it on your own using the same method. I'll just give you the answer so that you can check it out. Answer will be minus 2 by 5 tan inverse x by 2 plus 3 by 5 tan inverse x by 3 plus c. So these two are similar types. But in your NCRT, there is one sum, that is sum number 19, same exercise. That is exercise 7.5, sum number 19. That is 2x by x square plus 1, x square plus 3. Now this sum, please note, it looks very, very similar to the sum number 18, but it is completely different. Why? Because in the numerator you don't have x square. The above special type, I said both the numerator and denominator, both of them have to have the even powers of x. So sum number 19, obviously we will not deal in the same way. Here we will just substitute x square equal to say t, just like we did in the above sum. The difference, please note the difference. In the above sum, we did the substitution x square equal to t outside the integration. Here we are doing it as part of integration. So 2x dx equal to dt. So this becomes dt by t plus 1 t plus 3. Now this is partial fraction of type A that we had discussed initially. That is two linear factors not repeated. So you can now complete the sum. So and this is more or less I tried to cover the sums. So I hope it helps you. If you have any further problems with any of the sums, you can post them in the group. Okay, I'll try to do them and post the answer back. Okay, so I'll end this topic here.